Okay, so we're going to start the process of naming complex molecules involving transition metals and ligands. And we're going to start with the compounds that are neutral overall. That's not to say that there won't be charges that we'll be looking for. In fact, there will be charges to pay attention to. But the whole molecule, together is neutral. All right, one thing that we first need to emphasize is that when it comes down to ligands, if you have more than one present in the same transition metal complex, then you're going to have to specify how many of them you have by using the prefix di, tri, tetra, penta. Now, if it so happens that the ligand within its name contains the prefixes di, tri, or tetra as part of its own name, then to differentiate from that and to make it unambiguous, we will use the prefixes bis, monokis, tris, tetrakis, pentakis to emphasize that we have, that many ligands that contain within their name the prefixes di, tri, or tetra. The one that is by and large, the one you have to apply this rule to is going to be ethylene diamine because you have the prefix di within ethylene diamine, and that's the name of the entire molecule. So for that particular ligand, you will have to use the prefix bis, tris, tetrakis if you have more than one ethylene diamine present. And pretty much what we do is we're going to alphabetically place the ligands uh, in order, and after that we will basically end the name of the entire complex by stating the name of the metal, specifying its charge in Roman numerals. So the best way to go about this is to do a few examples. So let's get right to it and see how this goes. Okay, so here's one molecule. The whole thing is neutral. We don't have a charge written for this whole thing, so that means that this is a neutral complex. All right, so a few things to notice. First of all, we have the element right here, CO, which is transition metal cobalt. But also we have waters. We have three waters present in this complex. We have one carbonate present in the complex, and we have one chloride. Since each one of these ligands is bound to the transition metal, we have to drop the IDE endings, replace them with O's. We have to drop the E ending of polyatomics, replace it with O's. And for water, we have to use the special name aqua. And what we need to remember is that we have to place them alphabetically. So we have aqua for water. CO3 is going to be known as carbonato. And yes, we have three waters, so we're going to have to use the prefix tri to specify that there's three waters present. Then we have carbonato, which is the name of the CO3 ligand when bound to the transition metal. And then we have the ligand chloro. All right, now alphabetically speaking, this is only based on the names of the ligands, right? Not on the prefixes, but the names of the ligands. Alphabetically speaking, aqua comes first. Carbonato will have to come second because Ca comes before Ch, so chloro will be the last one. So naming this thing, we will start by saying triaqua, carbonato, chloro, in that order. And yes, this is actually all one word, so it might look kind of funky, but you kind of want to keep it like that. And then we were talking about cobalt, right? So the CO, that's cobalt. So we need to end the name of the molecule with the name of the metal, right? And the idea right here, which is kind of counterintuitive, is that even though we tend to start with the metal when drawing and writing these structures, we end the name with the name of the metal. We never start with the name of the metal. We always end it with the name of the metal. All right, now what we need to do is figure out the charge of the metal. And in order to do this, we have to actually remember and recall the charges of the ligands themselves. All right, so here we go. For water, you should remember that water has no charge, so that's got a charge of 0. But carbonato has a charge of 2 minus, so that you should remember. And chloride has a charge of 1 minus. So, looking at this thing, the fact that the whole thing is neutral, we have an overall charge of 3 minus coming from the one carbonato and the one chloro ligand. So that means that the charge of cobalt has to equate to ultimately the overall negative charge. But another way to look at this is that if you multiply the amount of the ligand or metal by its charge and then add up all of those values together, they should add up to the charge of the entire molecule. So we have one cobalt with a charge of X. We have three waters with a charge of 0, right? So you can see that here. We have one carbonato with a charge of -2 over here, and we have one chloro with a charge of -1. And notice that I'm adding all of those multiples together, and together they add up to 0. So we end up finding out ultimately that the value for the charge of cobalt has to be +3, which is how you will end up with a neutral complex. So what you basically do is you end the name of the molecule by saying triaqua carbonato chloro cobalt in parentheses 3. And this is how you would name the neutral compound. All right, let's do another example. Oh yeah, and one more thing before I forget. We have to recall what kind of ligands these are, right? So water is a monodentate ligand, so it will only occupy one site in the transition metal center. Since there's three waters, that's an occupation of three sites. Chloro is also monodentate, so having only one of those means that we will occupy one site. So right now we have four sites occupied. And carbonato could bind either twice or only once to the metal. But the common shapes are octahedral, which is based on 6 ligands, or tetrahedral / square planar, which is only 4 ligands. Since we already went past 4, what makes sense is for carbonato to be binding twice to the metal. Okay, and so that what that means is that this structure is actually going to be octahedral. And we could actually draw the shape of this molecule in a number of ways. We could actually have the waters on this particular face of the molecule. You can see kind of making a T shape with the waters. Or you could have the waters kind of taking on a corner of the tetrahedron, or one, hemisphere of the octahedron, excuse me. But in both instances, the carbonato ligand is bound twice to the metal center, right? And another way to look at it is that in one of the structures, the carbonato ligand is trans to the chloro ligand, right? So in opposite order. Or here you could say the carbonato and the chloro ligand are cis to each other, right? So this is how we can actually refer to them. And these are geometrical isomers because we are changing the overall shape of the molecules. Speaking of isomers, there's a few shapes or a few situations that I want you to be aware of. When dealing with the octahedral structure, you could have the situation where you have 3 sets of one ligand and 3 sets of a different ligand, in which case they can be positioned, 3 in one hemisphere, the other 3 in the opposite hemisphere. We call this the FAC isomer. Or you could actually have all 3 types of ligands forming the first T in one plane and the other 3 forming the second T on the perpendicular plane. We call this the mer isomer. And this will be actually prefixes that you would place in the name of the entire molecule. So in the case of the previous molecules, you will say FAC hyphen, triaqua, carbonato, chloro, cobalt 3, etc., etc. Right? So these are actually prefixes that will have to be applied if you have that type of shape in the molecule. All right, let's take a look at another example. Okay, we start with the first ligand. The first ligand is known as nitrate, but because it's part of the coordinative covalent complex, we refer to it as nitrito, or nitrato, excuse me. We have 2 of them, so we'll have to use the prefix di. And then we have this ligand, En. That's your good old ethylene diamine. And you probably do well to commit that naming and that spelling to memory. But you have 2 of them, and here you actually have the prefix di as part of the name. So here you're going to have to use the prefix bis, not di, because otherwise you'll get into ambiguous territory. All right, so we named this alphabetically. E comes before N, so the bis ethylene diamine, and notice that I'm using parentheses in front of the entire ethylene diamine to make it very obvious that the bis applies to only that unit. Followed by dinitrato. And now we have the name of the metal, and Mn is manganese. So we end this with the name of the metal, which is manganese. And now we have to figure out the charges. Nitrato has a charge of 1 minus, right? And we have two of them, so we'll have a 2 minus overall charge from the nitrato. Ethylenediamine is actually neutral, so we have no charge from that. And the charge of manganese is just X. So if we solve for X, we find out that the charge of manganese is 2 plus. So we input that as Roman numerals at the end of the metal name. All right, now looking at the occupations, ethylenediamine binds twice to the metal. Since we have two of them, that will account for a total of 4 sites being occupied. And since we have two nitratos present, each one of them will have to be bound to the metal only once. If they were to bind twice, you will basically end up with more than 6 sites occupied, which you don't really want to go past. All right, so you could, in essence, have a molecule where the nitrato ligands are trans to each other, or you could have them being cis to each other, right on the same, right next to each other, like 90 degrees apart from each other. So this is, some of the ways in which you can go about drawing the molecules. And to some degree, I'm going to ask you to look and identify the isomers possible for different molecules. Okay, let's do another one. All right, here we have the C2O4 ligand, which you should recognize as the oxalato ligand, which also bears a 2 minus charge. You also have the bromo ligand. There's two of them, so we're going to use the prefix di. Bromo comes before oxalato, so alphabetically we start with the dibromo, followed by the oxalato, and then we name the metal. And this metal has the name of platinum. All right, so we have dibromo oxalato platinum. Now to figure out the charge, we take account of the fact that oxalato is 2 minus and bromo is 1 minus. The charge of platinum so far is X because we don't know. We're about to find out. We have one platinum with a charge of X. We have one oxalato with a charge of 2 minus. And we have two bromos with a charge of 1 minus. So that means that we have overall a value of X minus 4 equals 0. Or in other words, the charge of platinum has to be 4 plus. And so the name of the molecule will have to be dibromo oxalato platinum 4 in Roman numerals. All right, in terms of occupancy, the oxalato ligand takes up 2 spots, and each one of the bromos take up 1 spot. So you have 4 spots being occupied. So here's where you could have either square planar or tetrahedral geometries taking place. And it won't be until the next lecture that you'll find out exactly how to determine which geometry takes hold of the structure. But one thing that I want to point out is that for your square planar structure, cis and trans isomerism is possible. But the tetrahedral structure does not have such type of isomerism. All right, now the last molecule that I kind of want to pinpoint right here, we have iron with CO. CO is known as carbonyl, and we have 5 of those, so we have to use the prefix penta. Since that's the only ligand, we will just call it pentacarbonyl. The name of the element is iron, so we ended by giving the name of the metal, which is iron. And as far as the charge goes, well, the charge of carbonyl is 0. And since that's the only ligand present, that means that the charge of the metal also has to be 0. And so here, since we don't really have a Roman numeral for 0, at least none that I'm aware of, here you would actually write 0 in parentheses after the name of the metal. And this can actually happen. In some cases, you could even have a metal with a negative charge. Those cases do happen from time to time, so just be aware of that. Those will not require Roman numerals, but you still have to write the charge of the metal. Alright, so we'll stop right here, and on the next video, we're going to examine ionic compounds, which are part of the coordinated covalent complexes.